So, you should be able to nicely see my screen, I hope. Not my screen, my whiteboard. And we're going to talk about how intercepts are performed. And again, this will be posted on a Instagram TV story later. But for right now, we're just going to talk, and I'll kind of walk you through some very introductory concepts on how an intercept is done. But first, I need to explain some concepts that you need so you can understand kind of what I'm talking about in the first place. So when we have some airspace that we are, well, let me back up just a tiny bit. This is going to be kind of like, obviously, at an unclassified level. For those of you who are listening, unclassified meaning not confidential, not secret, not top secret, anything like that. Obviously, we won't talk about anything classified. But there are some basic concepts of intercepts that are completely unclassified. So we won't be talking tactics at all, per se, here. We'll be talking about just kind of like how intercepts are performed. And so I'll be using red markers like this as the enemy, and blue markers like this as ourselves. And I'll use a black marker like this when I'm talking just kind of notes. And so when we are in an air-to-air environment and we've got two aircraft coming at each other, or maybe not even at each other, one's kind of out there and you're kind of intercepting it from a different direction, there's a three-dimensional problem you have to solve. You have to be able to solve not just which direction you're pointing, but what altitude you're at. That makes sense, right? So all of those things have to be kind of at least understood in where the problem is. So I'm going to start by explaining a couple concepts here. So let's say that we've got ourselves coming from like the southwest, and generally, let me give you a little bit of an understanding here. This spot, we're going to call that the center of our engagement area. That spot is as if right now we're looking straight down at it, which is actually what you're doing. Your phone, my phone that you're looking through right now is right here. You're looking down at this space like it's a map. So kind of look at it that way. You're looking down at a map. We call this, and I'm not even kidding, this is not a religious statement, but we call this the God's eye view. So the God's eye view of the engagement is the top-down view. And we actually use that. That's what the Top Gun manual recommends, and there is the actual Top Gun manual, multiple volumes of it that we have to practically memorize. But let's say we've got a group here in the northeast, and we're in the southwest. Obviously, this is north up. And in this case, I'm gonna go draw a little north up thing here. So this way is north. Right. So again, Iceman, tell me if you see any questions there that need to be clarified before we go on. Just go ahead and say it out loud, and I'll try to address those. But all right. So basically, this could be any distance right now. We don't know our distance. I'm going to define it right now, though. So let's say, for the sake of argument, that this is from the center. We are 10 miles from the center, and they are also 10 miles from the center, which is a total of, okay, quick math in public, 20 miles, right? So we're basically starting at a 20-mile spread, and this is actually a pretty easy setup. This is when we were in training back in flight school, but before we get our wings, first time, but I mean, you may have touched a Tomcat before now, but it's before you're actually flying a Tomcat. You're flying training aircraft that have either radars or simulated radars in them. And so you're looking at about a 20-mile set. And the way we actually set that up is we would start from a center point, basically together, and we'd say, you go to the southwest corner and you go to the northeast corner. When you get to the southwest corner of the box, you turn back around and start facing at the area that you're looking to start searching. Same thing with the north guy. When the north guy gets about 10 miles out, he's going to turn back in, and the fight will be on. So in this kind of environment, we would actually have radio. Again, this is a training environment right now, but we would have radio communication with each other on the same channel, and we would say, if we'd split out from the center, we'd go out to the outside edges, and we'd say turning in, and we're turning in. Well, both turn back in the same direction generally. And then once your wings level, because obviously every time you turn, you're backed over. So once your wings level, you'd say wings level, fights on. Fights on meaning that you are now running an engagement. This guy is doing what he's expected to do, and we are trying to find him. So all of this is simulating this kind of environment. Let's say we've got a coastline. This is just one possible explanation of why we're doing what we're doing. We've got a coastline, and we are looking to clear out some area here. Let's say maybe there's just for the sake of argument, let's say that there's an airfield here that we're looking to bomb. That's our generic representation of an airfield. It's two runways and a cross third runway. So we're trying to clear out this area so our bombers can come in behind us, or our strike aircraft can come in behind us. And of course, those of you who are familiar with a lot of different aircraft would know that many of us are multi-role, so it could be Tomcats, it could be whatever else. But if we're just thinking air-to-air environment here, this is what we're looking at. And so we want to clear out the space around this to keep it safe for those who are going in to deliver the air-to-ground ordnance. And we've got a radar, just again for the sake of argument, let's say our radar is going to look out off of our nose, which is our center line. That's our course, right? Off our nose, let's say it's looking 45 degrees right and 45 degrees left, just for general sake of argument. That's actually a pretty wide scan. We don't tend to scan that wide, but just for the sake of argument, we're looking in that area. So that means that anything over here we won't see, and anything over here we won't see, right? Because our radar is only looking in certain areas. But as you can see, even when you get out to 20 miles here, at 20 miles, I'll do a little quick math for you. We know some numbers. I'll tell you, a lot of this is actually math. And so if you're interested in actually doing this, if you're younger and interested in actually doing this, you better get pretty good math. But we have some ways to figure this out easily. At 20 miles, 1 degree is a third of a mile. So basically out here, a 90-degree arc, a third of a mile, we're actually scanning something like 30 miles wide on an arc, if you will, right? So that's a decent sized area of volume of space to sanitize, but we're also sanitizing from ground up to the surface, up to the highest altitudes we can. So something like 50,000 feet, maybe depending on what we just expect the threat might be. So we got to sanitize, that's the word we use, sanitize this volume of space with our radar. It's sometimes a little bit challenging, and if we have a wingman, we might divide up that responsibility. Someone might be looking high and someone might be looking low, and then you kind of cross in the middle of it. Or the real extra thing is if we have some other kind of aircraft back here, or let's say a ship. If we are in the littoral environment, we actually might have a ship out here that is, again, drawing upside down, I apologize, but a ship with maybe an Aegis radar, which is actually really good at sanitizing a very large volume of space. And it could actually be telling us what's out here as well. So let's go for this example that we're not only using our own radar, we are actually using the ship's radar as well. So the ship, sorry, to make it a little bit clearer, we're not actually seeing the ship's radar. Again, for basic employment, let's say we're not. Oops, I lost my pen on the floor. Okay, so we're going to go a little bit more narrower of a look here. We're going to go like 30 degrees off our nose, or 30 degrees off of the center line of what we're looking at. And now we're trying to sanitize this space, and we get a call from the ship that says something like, well, we want a picture, and so we would ask for a picture. We'd say, hey, whoever the ship is, let's call it, I don't know, Rough Rider. That's the call sign for the Theodore Roosevelt, which I did a couple deployments on. So Rough Rider picture. And so Rough Rider would say, Rough Rider picture, single group, if they're actually tracking this guy out here. So remember, he's here. Single group, BRA, and that means bearing, range, and altitude. B-R-A, BRA, single group BRA. And what I have to explain here is a couple concepts now as well. So bearing is relative to north. Now, I drew the north arrow up here, basically showing you that north is this way. But again, we are here. So our north from where we are is this direction. Single group bra, so bearing from north, it looks like about, I don't know, 30 degrees. So we're going to say this guy is up here. He's up here at 0, drawing upside down, sorry, 030. He's 030 from north relative to where we are. Single group bra is 030, and then range is, well, we just told you it's about 20 miles. So we're going to say at, sorry, drawing upside down again, 20, and altitude. And so in this case, they might not know the exact altitude. They might say high, medium, low, something along those lines. But basically the idea is that they're going to tell you the best they can. Oops, I didn't mean to move that. Pardon me. Get that back on there. There you go. They're going to tell you the best they can. So let's say for right now that they're just going to tell us that this guy is medium altitude. And that would mean something probably above about 10,000 feet and below like 40. So 10 to 40,000 feet, that's the area we want to point our radar at. So in the cockpit here, I would now scan over, I'd adjust my scan volume to make sure that the center line of my scan is on that bearing. So I'd make my center line 030, which is looking relatively close to where he is. Let's say that this is actually 030, like that. And that's exactly the heading I'm going right now. 030, 20, and that's actually where he is. And he's medium altitude. So again, he's something like 10, 20, 30,000 feet. Let's say he's actually 25,000 feet, and I'm looking for him there. On my radar, I'm going to have to draw a slightly different drawing here. So I'm going to draw that down here in the bottom. I actually see a scope. How to draw this right? How to draw this more easily? So I'm going to see something like this. And I know where my central scan volume is right now, is on my nose. And somewhere out here, this is distance away from me, so something like a very short distance, and this is a very long distance, again, depending on which radar we are operating on. That could be something, if it's a Tomcat, a long way away, over 100 miles. If it's a training radar like we were using, which is actually an F-16 radar, or something more like 30, I think it's like 40 miles. It was the outer range out here. So I'm on a 40-mile scale. If you're used to using a GPS in your car, you're familiar with this kind of an idea here. I would have it out here where the thing I'm looking for out here at 20 miles is somewhere kind of in the middle of the scope, not on the outer edge because I don't want it to fall off. So let's say I got myself on a 40-mile scale here, right? Which means that this would show up, if I start seeing a contact, something about here, kind of in the middle of my scope. Again, this is the scope is showing me a God's eye view too, but only a portion of it because my radar isn't looking behind me, it's not looking directly beneath me, and I really can't see really close to me either, unless I'm in a different mode. So I'm looking this way, and I'm going to start to see a little bit of a blip here. Now what I can do is I can actually then scan in my radar a little bit closer and say, okay, I think I've got it. I say single contact, single group, and then I would actually call out this specific location. So I put my cursor over it, which looks something like that, and I would see what information that's giving me. Well, that's giving me now, this takes a little bit of time, and remember, of course, we're moving as this is all happening. We're not standing still, right? So let's say 10, 15 seconds has already gone in this in this time. So we've actually closed that distance somewhat, and I'll do a little bit of math right here just to talk about how much we've closed. But let's say we've already shortened by maybe a mile or two, probably 3, something like that. So I'm going to say I'm seeing something here like 035. I'm sorry, I'm doing this a little bit upside down and backwards, but let's say 035, 27 hits, HITS, meaning I'm seeing hits, radar hits, 27,000, or Angels 27. So I'm seeing hits at BRA 035. That's a little bit too farther to the east, a little bit closer. 27, as in miles, and then, like I said, something like 27,000 feet, whatever it actually happens to be. The ship would come back and say, good contact or not good contact. Basically, they're going to tell you whether or not that's the same thing they're seeing. And then they would tell you how that contact is declared. Well, obviously, if it's a friendly, you don't want to intercept it, but they wouldn't be telling you to go intercept a friendly anyway. They would be going to telling you to intercept some kind of bogey, which is an unidentified aircraft, a bandit, which is presumed hostile, or actually hostile. Let's say, again, for the sake of argument here, that they're going to declare this aircraft hostile right now. So now, if we are fairly certain, I'm sorry, wrong color here, we're fairly certain that the only thing we're going out here is this one bandit, we're actually going to close in even further and go to maybe like a 10-degree scan. Now that scan distance means something here. The scan size means something. Because you have a radar, and this is an older style radar now, a classic style radar, where the antenna is constantly doing this, basically swinging back and forth, right? So if it's got to go 45 degrees one side and 45 degrees the other, it's got 90 degrees to swing, and it takes a while for it to get back and forth. If you get down to a 30-degree scan, it's doing it faster. On a 10-degree scan, it's doing it a lot faster. So the faster your scan is updating, the better information you're getting off of this contact. The more updated information you get off this contact, and it's less likely to move out of what we call your scan volume, the volume of airspace you're scanning. So let's see, how are we doing here? We're about 15 minutes in. I suspect there have probably been some questions, but Iceman, just can you give me a quick warm fuzzy, if you will? Have I lost anybody completely yet?
Yeah, that's fine.
Okay, good deal. We're good. All right, so I would take it down to a further detail. And let me talk a little bit about speed here. So I know it's unusual for most of you. Most people watching this probably won't be familiar with traveling 300 knots. But we're doing these intercepts, even in training, at about 300 knots. We actually might speed up a little bit. We might slow down a little bit. But we're doing these at kind of a relatively constant 300 knots. Quick math for you. 300 knots. Pardon me. 300 knots is what? Oof. I'm drawing backwards. Right, I gotta make this backwards. So 300 knots equals 300 nautical miles per hour. And since a mile per hour is, there's 60 minutes in an hour, that's approximately, it is 5 miles per minute. So 300 knots equals 5 miles per minute. Does I draw this backwards again? 5 nautical miles per minute. So 5 nautical miles per minute. Well, again, we were only 20 miles apart to start with here. It's pretty close, actually, for an air-to-air set. So that means that your downrange travel, this is all going to happen in 2 minutes. Why does that work out? Again, 20 miles, traveling 5 miles to the minute, 20 divided by 5 is 4 minutes. That means you would go this different distance in 4 minutes. Same thing. So he's also traveling on, again, for training here, he's going also 300 knots, which means he's also going there. So in other words, if you didn't do anything, you would meet somewhere around the middle here in about 2 minutes. Well, what I just talked you through is about 15 to 20 seconds. So it's like, let's say 30 seconds. So in that 30 seconds, I've traveled 2.5 miles, he's traveled 2.5 miles, and that means we're actually only 15 miles apart now. So 2.5 plus 2.5 is 5. And 20 miles total to start means that we're only 5 miles apart now. So the way we draw this out, I'm gonna take our radar lines off here because they're cluttering up a little bit. But the way we draw out an intercept, I had to kind of spend a little bit of time here giving you some general concepts of how this works. But the way we actually draw out an intercept is when we actually have equally spaced sized drawings to represent a unit of time. So I'm going to do these based on basically half a minute. So after this first half a minute, we have traveled this far, and the arrow is showing you both the magnitude and the speed at which the plane is traveling here. The magnitude of the arrow is basically showing your speed, and my arrows are ugly. And if any of my Top Gun friends are watching this, they would be laughing at me right now because I'm drawing badly. Yes, I'm not even kidding. We actually practice drawing arrows to get this right. So In a debrief, we would want to draw this basically to scale. If this is 20 miles, this is our arrow size for approximately getting out to what we would expect to happen. So we've traveled a little bit closer. So again, we're only 15 miles apart. Our bogey has actually moved straight down in this general direction. So now he's more like here. And I would continue to have my cursors on him to keep updating. Let's say I want to take that commit, meaning I am going to commit to intercept this aircraft, meaning that I'm taking responsibility for it. So we're now at 15 miles. Again, in a Tomcat, I'm feeling really threatened if I'm at 15 miles. If this is an actual enemy aircraft at 15 miles, I want this problem way solved by now, or at least mostly solved by now. But at this point, we haven't actually said whether this is a hostile aircraft or not. So I've taken the commit, and I'm basically saying that I'm going to prosecute this intercept to whatever extent my control is wanting me to do that. So let's say, just for the sake of argument, that our ship down here, our ground controller has now been able to get some information to say that this is actually a hostile aircraft. So hostile meaning, depending on our rules of engagement, we can destroy it. So there's a couple things we might do here. If we already know it's hostile, chances are we would go ahead and launch a missile right now. So I'm going to represent that by showing a missile inbound. Now, these missiles are a lot faster than our aircraft. By not an order of magnitude, by a couple of times, depending on what missile we're talking about. If we're talking about a Phoenix missile, they go really fast. Even if we're talking about a Sparrow or an AMRAAM's AIM-120, they're going significantly faster than our aircraft. So they're going to get to this target pretty fast. Now, if you're familiar with our types of missiles, you may know that AMRAAM, the three missiles I just mentioned, AMRAAM, Sparrow, and Phoenix. Phoenix is, of course, not in the inventory anymore because Tomcats are the only aircraft to fly them, to launch them and fly them, operationally at least. But they are all radar guided, meaning they have to have some amount of reflected radar energy off of this aircraft to be received by this missile so that it can track. Now, that doesn't mean they just automatically go straight at the aircraft. They actually are quite a bit smarter than that, and they perform an intercept themselves on this aircraft, knowing that this aircraft is moving as well. And so the missiles have a good amount of intelligence built into them to be able to prosecute that intercept and make it happen. But they're going to get there. It's going to get to this aircraft some point before we do. So what we want to do, now that let's say we've launched the missile, we want to slow our downrange travel because there's a good possibility that this aircraft has also launched the missile at us. They may have also said, wow, we have a hostile aircraft down here coming to, remember, this is their territory here. We have a hostile aircraft coming into our territory. So we don't want that to happen. So let's say, for the sake of argument, that they also launched the missile. Well, they launched a shorter range missile than we did, but we're going to take an offset. We're going to actually go over here. We're going to turn in our next minute, or next 30 seconds. We're doing 30-second arrows, right? So in our next 30 seconds, we're going to turn to the farthest angle that we can and still have our radar following. So we're going to make, for the sake of argument, let's say 75 degrees off our nose. There's 90. So 75 degrees off our nose, bam, 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 like this. This is the farthest that our radar is able to look. And we don't want our gimbal, we call it gimbaling our radar, making it so that it can't continue to track on this aircraft anymore. So we would actually go even a little bit farther than this. I'm not going to redraw it for the sake of time, but let's say that we are actually looking something like this. And we've also taken what we're going to refer to as a single target track, STT. I've taken an STT, and you'll hear that phrase sometimes. I've taken a single target track, meaning that my radar is now tracking on this whatever radar return I had out there. Because it is able to see a very big difference in the amount of energy coming off of the aircraft versus what else is out there, it can continue to maintain track just by seeing how much energy is out there, how much energy is being returned. But Also, as I'm getting closer, again, at this point we were 15 miles, so I probably changed my scale. I'm going to leave these on here for just a second. I went down to a 20-mile scale probably, right? That would make a lot of sense for being about 15 miles apart. So now I'm down to 20-mile scale. So you would expect them to be somewhere up, you'd expect them to be somewhere up here on a 20-mile scale. But we turned hard to our left, hard to our right. So now we are looking off to our left, if you can think about it that way. So this target out here at 15 miles is actually all the way over here on the side of our scope now. The radar is seeing it way over on the other side of our scope because we turned. And if you can think about this, the reason we do this is because that's stopping our downrange travel. The farther the closer we go to, think about like with respect to the shore here. If we go completely parallel to the shore, we're not getting any closer to the shore, right? Same sort of thing here. If we turn as far as we can away from our downrange travel against this target aircraft, that's actually going to make it so it's farther to get, and it's harder for them to get to us because we already have a missile in flight. Now I'm going to draw one other thing to slightly more to scale, again, because this missile moves faster than we do. Let's say, for the sake of argument, it goes twice as far as we do in the same 30 seconds. And their missile is also going twice as far. But it was launched going in this direction because that's where we were. So it's doing something like this. That's how far their missile's going in that next 30 seconds. But because they are working on ground intercept, they're not actually necessarily having their own airborne radar, or their airborne radar isn't tracking as well, perhaps. They're going to continue to go nose on to us. So what that means is they're going to just basically point right at us instead of doing an offset themselves in some other direction. So what they're doing a slightly different target, and they're just going to kind of point right at us at the same distance. At the same speed. So now their missile, I'm just going to kind of walk you through this now. I'm going to do each individual time step. So this was the next 30 seconds. This is probably a bit too far. Go a little bit closer here. The next 30 seconds, what we're going to do here, we're going to continue our offset, trying to keep him walking down the left side of our scope, if you will. And he's not going to be coming as quickly anymore because we've taken an offset that's make this downrange travel not go so fast. So we're going to continue to arc kind of out this direction generally. Oop, that's black. It is important to keep our colors because that way it keeps it all straight. So we're going to continue to arc over this way. Our missile is also going to track on him. So it started off in this direction. It's going about twice as far, and it's going to start pulling a little bit of lead because it sees what he's doing. It sees that he's turning off to the left. He's going to continue to try to follow us. Again, this is 30 seconds of travel. Its missile is going to try to track on us, but it's already started to lose a little bit of its advantage, right? Because it's kind of far away. Somewhere around the midpoint here, these missiles are going to actually not cross. I'm going to draw a little bit of a break, showing that they are getting there at different times. They don't hit each other. We don't have missiles intercepting missiles. But in the next 30 seconds, we're going to win this battle. It's actually pretty easy because all we're doing is we continue to maintain as much of an offset as we can to make sure that we are staying away from our enemy aircraft. He continues to track on us. Unbeknownst to him, he, about 15 seconds into this path, gets hit. And he's down. And his missile goes stupid because it has no more radar energy. It just goes off in some direction. Who knows where it goes. And we just won that engagement. So that is a very basic intercept. Where we got it declared as hostile. We got them declared as hostile. I'm going to draw a red diamond over them right here, saying that that's when they went hostile. And I'm showing that we fired F1, Fox 1. It's a radar-guided what am I trying to say? I've lost my term here. It's a guided missile. It has to retain missile guidance on its way. It does not have its own radar inside, so it's got to rely on our radar to provide its guidance. But in this path, so how far apart if we started 30 miles apart here, my hand span, we ended like 10. I'm sorry, we started 20. So we ended like 7. So we actually saw this tracking down, if this is down here on our scope, if this is 20 miles, we actually saw it get to about here, and then it would just disappear. It would literally just come off the scope. And if we're only 7 miles away, I'd be looking out my left side of my window, and I would see a big fireball. So it'd be pretty obvious that we just had a successful intercept. But the intercept would not stop there, because we can't assume just because we saw a fireball that it was necessarily the end of the intercept. What if there was actually 2 aircraft there? Again, remember we got this, it was a single group, was what it was called. So we're going to assume that there's a second aircraft. But I see we've been going about 35 minutes, so I should probably stop the discussion here right now.